Hello everyone, this is Vashishta from Aerobay section. Today I am going to explain about analysis of fluid, flow field and a sound field characteristic of 2D airfoil based on FLUENT. It is a topic from aerodynamics. So basically, when we take an airfoil, we have to analyze it so that it gives the pressure conditions and the velocity conditions, which provides us a good lift and drag coefficients. So we use a software called ANSYS or any other software which contains Fluent, and they compute and they analyze the shape of an airfoil and gives us the results of sound field and another flow fields. Coming to the introduction, part, airfoil is one of the major components for wind turbine blades. 2D numerical simulations of NACA 4412 airfoil was carried out based on LES method by using Fluent software. And also we can see airfoil is a main component of a wing. And to give the main factor of large scale separation and vortex were found out by applying precision finite volume methods and simple algorithms. According to the characteristics of the frequency spectrum of the noise signal and flow field, it was found that the frequency ranges of the noise source between 330 Hz and 470 Hz by using FVH acoustic model of fluent aeroacoustic software. It provides a reliable theoretical basis for the optimum design and the noise reduction of a wind turbine and airfoil. Generally, we can say that these types of airfoils will give us, and I have taken this from a Chinese one and I have translated it. And the wind turbines produces noise when they are working. They cause noise by pollution and vibrations to surroundings. Our aim is to reduce the noise by creating a mechanism with low frequency noise and turbulent noise. Because airfoils are widely used in fluid frame in wind turbines, if blade has good aerodynamics, it will give high efficiency and low noise for wind turbines. So the research is to calculate the noise by formulas and analysis. The noise of a NACA 002 is estimated by semi-empirical formulas under different angle of attack. And also we use CFD analysis for boundary layer mesh and structural mesh. The unsteady flow distribution of airfoil by numerical simulations can also be done. And coming to the analysis of airfoil flow field characteristic based on large eddy simulations. Due to large radius of a leading edge of airfoil, the surface boundary layer is easily separated to form vortex or turbulence, and the formation and the rupture of the vortex affect the flow field distribution at the same time, which is one of the main reasons for wind turbine stalls, flutter, noise, and other phenomena. The unsteady flow field distribution of two-dimensional airfoil can be obtained by direct numerical simulations (DNS). Below step average simulations (RNS) and large eddy numerical simulations (LES). Among them, direct numerical simulations is currently limited by computer resources, only applied to simple turbulence with low Reynolds numbers. The time average numerical simulations give the statistical average of the turbulent flow field, which can effectively simulate the flow of the attached boundary layer. But the time average numerical simulations lack separate analysis and it lost in the flow field calculations. The time domain and the frequency information clues related to the noise are obtained, while the large eddy simulation decomposes the physical quantities in the turbulent field into larger scale turbulent eddies. The main determine the mainly that mainly determine the turbulent characteristics and small eddies that play dissipative role and are approximately uniform and isotropic through filter functions. Large-scale vortices that are greatly affected by the flow boundary can be directly calculated with the small-scale vortices that are less affected by the boundary are simulated by the closed mode of sublative stress. After filtering the large eddy simulation transient equation is expressed as dou by dou t of sigma un plus dou by dou xj sigma rho ui uj is equal to minus dou p by dou xi. So the model establishment and machine. So when we take a dark of 441 to Airfoil with a chord length of 1 meter and perform geometrical modeling through the preprocessor gambit and the fluid software, the two-dimensional airfoil section is shown below. This is the 2D geometry of two-dimensional geometry of an airfoil NACO 4412. In the numerical calculation, the grid is generated by the method of multi-mode modeling. The calculation range is divided into incoming flow section, the rotor section, and the wake section. The key is to simulating the unsteady flow field of airfoil is to accurately simulate the separation phenomena of a boundary layer. To make the flow field fully developed, the inlet of the flow section and the outlet of the wake section in the future are taken as 11.5 times and 21 times the chord length respectively. Through the geometric shape of an airfoil, the thickness of the boundary layer grid is reasonably arranged and the structural grid is and the overall calculation area is taken as C-shaped grid and considering the flow field of the front and rear edges of the special shaped airfoil has great influence on the numerical simulation of an airfoil. In the process of grid calculation, the measures near the airfoil are locally intensified. As we can see, this is the particular mesh of an airfoil. The number of meshes is 39908. And determining boundary conditions. The incoming wind speed at infinity is set to the inlet boundary. The outlet is to be fully developed pressure outlet conditions and the gauge pressure is given as 0. The periodic boundary conditions are used for span direction considering that the airfoil surface satisfies the software so no slip conditions. The immersion is applied boundary method set to the incoming velocity to 50 meter per second. The angle of attack is 10 degrees and the residual of each item are less than 10 degrees. The sublattice model is used to as the dynamics microorganism model and the solve of discrimination. Analysis of calculation results. The calculation is based on earliest method and the simple algorithm of the high precision finite volume method is used to solve the calculation and the flow field distribution at the 100 time step. That is TSON is given. Here we can see the pressure distribution in airfoil and the velocity vector at 10 degree of angle of attack. Here we can see there's a more velocity at upper and less velocity. And the pressure differentials are also shown here with the flow field at a 10 degrees angle of attack. Airfoil sound field analysis based on FPH method. Irregular white body noise is generated by the interaction between the irregular boundary layer and the trailing edge. Brooks et al. Divided it into 5 parts according to the generation mechanism of airfoil noise. and give the corresponding sound pressure level prediction formula trailing edge noise in the formula D. The boundary layer thickness of the pressure surface are the empirical functions of the Strouhal number, Reynolds number, and the angle of attack respectively. Separate flow noise. The trailing edge noise is the superposition of the pressure surface noise SPL and the suction surface noise SPLA on the airfoil boundary layer. These are the formulas regarding SPL, TBL, P, and 10 log S10 SPL P by 10 plus SPLS by 10. BFW specific model which can predict the sound radiation of objects of any shape based on the far field pressure and the noise sources. The model is related to the closed integral surface and the spectral characteristic near the airfoil that are examined. And this is the expression given below. These are the pressure pulses and the sound pressure specters on the monitoring points. Coming to the conclusion, in this paper, through the finite volume and simple algorithm of large eddy numerical simulation of a FLUENT software, the unstudied turbulence simulation of a NACA 4412 two-dimensional airfoil is carried out. And the flow field distribution of the 100th time step is obtained, and the flow field of the airfoil generating noise is analyzed. The FWH aero oscillating model considers the spectral characteristic near the airfoil, so it can give more realistic results than other methods. Therefore, according to the spectral characteristics of the airfoil, the theory of self-generated noise and the FWH escorting model, the two-dimensional airfoil is mainly concentrated in the frequency range of 330 to 470 Hz, which is same as the measured data provided by literature. So, which is fully shows as the calculation theory research method adopted are accurate. So, this is all about my explanation. Thank you.